Welcome to the lecture module on optics. In the last couple of lectures, we discussed the Young's double slit experiment and brought out some salient features of interference, the phenomena of interference. Today we will discuss another phenomena which is closely related to interference called the diffraction. So, diffraction of light. Diffraction of light refers to, so let me first give a sort of definition of diffraction. So, diffraction of light refers to the spreading of light into the geometric shadow of an obstacle or an aperture in the path of propagation of light. Spreading of light. If the beam of light is monochromatic, that is, if the incident beam of light is monochromatic, then one can see bright and dark fringes or rings or patterns depending on the geometry of the obstacle. We will try to understand these concepts in this lecture and the following lecture. So, let me first try to explain what is this spreading of light into the geometric shadow of an obstacle. Spreading of light into the geometric shadow of an obstacle. Consider a parallel beam of light incident on a screen. Here is a screen, a parallel beam of light incident on a screen. Now, what you see here is the bright spot of the light which is incident on this. Now, if we bring a wedge here, a triangular shaped wedge with a sharp edge here, a straight edge here, we try to bring it from below like this, that is to intercept the beam, cut the beam, then there will be a shadow, the geometric shadow that we get. So, let us try to appreciate this if we look at the beam incident in 2 dimension. It will become more clear if we look in 2 dimension. So, let me show you a diagram where we see the incident beam. So, the incident beam is here, this is a parallel incident beam, and we have introduced this wedge from below. So, it is cutting or blocking part of the incident beam like this. So, part of the beam is incident on the screen and part of the beam is blocked by the wedge which is introduced from below. It is an obstacle, wedge shaped obstacle which is introduced from here. Considering ray optics or the rectilinear propagation of light, what we expect here is half of it is bright and half of it is dark, because this area, the area below this dotted line here, this region is blocked by this aperture, and therefore, we should get a shadow here, shadow of the aperture. We have considered a parallel beam of incident light, therefore, up to this we must have the shadow and above that we must have bright region. In other words, if we were to see the intensity distribution, we should have seen a step function like this, that is, intensity is uniform across here and then here it is 0. Oh, let me draw here and show it what I mean by this intensity distribution here. So, here is the incident light. So, I am enlarging it and showing. So, this is the parallel beam of light which is incident, and we are introducing a wedge from below. So, we have introduced a wedge. So, the wedge is, so this is the wedge. So, light which is up to this would all come here onto the screen. So, from geometric optics or from the rectilinear propagation of light. So, if this is the screen on which light is incident, then we would expect a shadow. So, this region here is called, this region is called the shadow of the obstacle, shadow. So, I had used this word shadow of the obstacle. So, obstacle is this wedge, shadow of the obstacle. So, this region, that is the region below here. So, this is the shadow of the obstacle. from the rectilinear propagation of light, we should have had a shadow here and bright light on the other side. In other words, if I were to plot the intensity distribution, so suppose this direction is x direction, x, then if I plot the intensity distribution on the screen. So, this is I of x, intensity distribution I of x, then I should get up to this, I must have a uniform intensity. If this beam is of uniform intensity in the cross section, then I should have uniform intensity up to this point here and then 0 intensity. So, beyond this it is 0. So, uniform intensity here and then 0. But what we see actually is, I will let me use a different color. So, what we see is there is some light which comes into the geometric distribution, the geometric shadow here. The light distribution shows some variation like this, and then you have some light entering this shadow. This is the shadow region. I expect it to be a shadow region, but there is some light intensity in this shadow region. This is because of the phenomena of diffraction. In other words, let us see the definition again. Diffraction refers to the spreading of light into the geometric shadow of an obstacle in the path of propagation of light. I have now explained it with the help of this. Path of propagation of light, there is an obstacle which has been introduced and light has spread into these regions, light has spread. That is why you have a finite intensity here. Intensity is not 0 in the shadow, there is a certain amount of intensity in the shadow, and this is because of diffraction. So, the phenomena of diffraction as I defined in the sentence. So, diffraction refers to spreading of light into the geometric shadow of an obstacle. Now, we come back to this diagram here. So, I will show the pre-drawn diagram here. So, here is the incident beam, parallel beam, this is the shadow. What you see is a part of light, some amount of light. So, this is the geometric shadow. So, this is the shadow region. I have exactly plotted behind this. So, this line here is the same. I should have had light like a box here, but what we see is the intensity distribution across this screen here. Here it is just like a box, intensity is maximum, uniform and then 0. If I were to plot the intensity across this, it would be uniform and 0 outside. But what we see is there is some intensity in the geometric shadow of this obstacle, and this is diffraction. The beam undergoes diffraction at the straight edge. Please see, this is in 2D. We recall the figure here. So, this is the straight edge that we are referring to. This is a wedge shaped obstacle which has a straight edge here. It need not have a straight edge, but we have considered for simplicity a straight edge, and therefore, light enters into the geometric, the beam undergoes diffraction at the straight edge at the top end of the wedge, I hope I have explained the figure here. So, the intensity distribution across the beam on the screen. Now, suppose I had introduced just one wedge from here. Suppose I introduce another wedge from here, from the top. Suppose I introduce another wedge, then what we will get is a slit. So, we will get a slit here. So, if we introduce another wedge, we get a slit. So, that is what I am showing in the next diagram here, that here is the same beam, the parallel beam which is incident. There was one wedge earlier, now we have a second wedge from the top. So, this has resulted in a slit here, and the rectilinear propagation of light would have seen that light is incident only corresponding to this gap, but in practice if you see there will be some amount of light into the geometric shadow here as well as the geometric shadow here, shadow of the obstacle here. And if you measure the intensity distribution, you see some intensity variation here in this region and a intensity, a little bit of intensity into the geometric shadow on both the sides. Recall the earlier figure. So, let me show the earlier figure. Here there was light entering the geometric shadow on one side. So, now I have shown the edge wedge from both the sides to make a slit. Now, we see that light enters the geometric shadow here. This is a case where I have taken this width of the slit. So, this is the slit W or A, we will use A later on W. The wavelength of light lambda is much less than W and W is less than D. D is the beam diameter and the width of the slit is smaller, that is why it is blocking part of the beam, and this leads to onset of diffraction effects. We have started seeing diffraction effects. If this were not there, we should have got a box type of response, that is intensity uniform across this and then 0 outside, but we see that there is some amount of intensity entering into the geometric shadow. What happens if we further reduce the slit width W? If we reduce this slit width further, so that is what we will see, and what we will get is the single slit diffraction. So, here is what I am showing as the single slit diffraction. First look at the diagram. So, the same parallel beam of light, same two wedges, but now the separation between the wedges is very small. I have used the symbol A to be consistent with the book, textbook, and therefore, the wedges are separated by a small separation A. The separation A is now of the order of wavelength of light, and then instead of just having a box like pattern here, what we have is a intensity maxima and minima on the screen. We get intensity, we observe intensity maxima and minima on the screen. The first minima here, as we will see later, is given by lambda by A. That is, if we plot the angular distribution, this is I of theta, this is not x, this is I of theta, theta is the angle here. So, with respect to this aperture, if I plot a ray like this, then this angle is theta, this is the theta. So, I of theta varies like this, we will see this shortly, but what is important is as you reduce the slit width, you not only see light going into the geometric shadow, but also you start seeing intensity maximas and minimas, just like in the case of interference, except that here we see that the maximas do not come back again up to this. The maximas are very small maximas, very low intensity maximas, but we do see intensity minimas, intensity zeros and small maximas in the geometric shadow, and this is called diffraction. And because we have used a slit here, a narrow slit with the dimension of the order of wavelength, we call this pattern as single slit diffraction. So, what we see, so this is the front view. So, this is the front view now, the slit is here and the light is incident normally onto this, and this is the screen behind the slit, the screen which is behind the slit, screen which is, so you see intensity maximas here. So, the central maxima, central bright fringe here has very high intensity as compared to the sides. So, on the screen behind you will see straight line fringes like this on the screen, and this is called single slit diffraction. So, I have just introduced what is diffraction and what is meant by single slit diffraction. So, let us see this in more detail. So, let us recall first the Young's double slit experiment, because here also we have a slit and in Young's experiment we had 2 slits. So, let us recall the Young's double slit experiment and see what is the difference here in comparison to the Young's double slit experiment. So, recall Young's double slit experiment. So, I have shown the Young's double slit experiment which we had studied in great detail. So, first look at this part. So, here is the 2 sources S1 and S2, point sources S1 and S2, and then this is the screen placed at a distance d. The sources are separated by a distance small d, and we had R1 is the path length here, R2 is the path length. Therefore, there was a path difference at an arbitrary point P, there is a path difference between the 2 sources here. The light reaching from the 2 sources has a path difference, and therefore, there is a corresponding phase difference which is k times R2 minus R1. Recall that this k is 2 pi by lambda, the phase constant. K into R2 minus R1 gives you the phase difference delta. And then we have seen that the intensity distribution here is given by I of delta. We have derived this expression, I of delta is equal to 4 I 0 cos square delta by 2, and then it varies like this. If you plot the intensity distribution, it varies sinusoidally like this. Every fringe is of the same intensity as per this expression. According to this expression, we have bright dark rings. So, I have shown the corresponding intensity pattern here. So, the dark ring corresponding to this and the bright ring corresponds to this region, bright, dark, bright. So, we have bright dark rings fringes in the case of the Young's double slit experiment. And I also showed you a diagram, a computer generated diagram here. So, which showed the bright dark fringes in a Young's double slit experiment. I had taken typical parameters of typical of experimental arrangement, and then I calculated these fringe patterns which are shown here. There is something which we did not discuss earlier is, if you see carefully, the central part, the contrast is high, bright dark, but as you go further and further, the contrast drops down, the brightness becomes lower and lower. As you can see, this is very bright, but if you go to a fringe which is here, the brightness is continuously reducing. The darkness is the same, the minima is the same, that is minimas are intensity zeros, but the brightness is decreasing as you go along x, that is on the screen. As you go away from the center point, then the brightness of the fringes reduce. We did not discuss about this variation in the intensity. Now, we will see that this is because of diffraction. What we see, the intensity variation in the bright fringes in the case of Young's double slit experiment, as you go away from the central fringe, is because of diffraction. We will see this carefully. Okay. So, now let me look at this more carefully, and why does this happen? Why do we get, in the case of, suppose this was the Young's double slit experiment. In this, the most important point to note is, we had treated these slits S1 and S2 as point sources, but we know that in practice no slit or no aperture can be a point. There is a finite area associated with the aperture or with the slit, and this we have not considered in treating the Young's double slit experiment. In analyzing the Young's double slit experiment, as we did earlier, we did not consider the finite width of these sources. So, let us now look at the each slit here, one slit at a time, and see what is the effect of the finite width of the source. So, let us see this in the next slide. So, here, so what I have shown, so let us look at this diagram here, let us look at this diagram. The finite width A of the slit. So, this is one of the slits S1 and S2, there are two slits in the Young's double slit experiment. So, if you look at one of the slits, then there is a finite width of the source here, which means the secondary source on this slit here, the secondary sourcelets, the point sources on the secondary wavelets which emanate from this, there is a finite path difference at P. At the point P, this there is a path difference, this is smaller compared to this distance. So, if I call this as R1 and from this extreme end of the slit, so the upper end of the slit S to the point P and the lower end of the slit to the point P, because I am now considering a finite width A for the slit, then there is a finite difference in the path because of a finite width of A, and therefore, if there is a path difference, then there is a phase difference. If there is a phase difference, then the intensity at the point P will get affected by the phase difference. So, if I enlarge this, so this is when the screen is kept at a certain distance. Consider now the screen kept at a large distance. So, let us look at this case here, the second case, the same diagram, but I have now shown it enlarged view. So, enlarged view when L is large, when L, this separation is large. When this separation is large, so this screen is sitting at a large distance, then these rays, all the rays which are drawn here, all the lines which are drawn here appear almost parallel. They appear almost parallel because the L is now very large. However, what we see is this is the aperture size A, this is the incident beam, and inside the aperture we have shown different point sources here, and therefore, if we show these point sources at equally spaced point sources, if we consider equally spaced, actually there are infinite number of point sources, but if we consider a finite number of equally spaced point sources, and then we can in the analysis, actually this is the way we start, and then we allow n to go to infinity. That means, initially n number of point sources and then n is allowed to go to infinity. Now, coming back to the discussion, if the screen is at a large distance, we can treat all these rays emanating from the point sources as parallel rays. And then what we see is that there is a, if we look at the first ray here and the last ray here, then we see that there is an additional path difference here. So, there is a path difference. This is the path difference between this and this, because this is a plane wave front, it is a parallel beam which is going here, because we have considered parallel rays. If we consider parallel rays at any particular angle theta, that means it has a plane wave front, then there is a path difference between this ray here, this path and this path, and that is this path difference. If theta is this angle, theta is the angle with the horizontal, then this path difference can be shown. If this is A, then the path difference delta, that is the path difference delta is equal to, so we can show that delta is equal to A sin theta. So, let me write here itself. So, delta here is equal to A sin theta. So, we can show that the path difference, now I have picked up only these, the last one and the first one, but there is an equal path difference among these. So, between any two adjacent rays there is a finite path difference. When there is a finite path difference, there will be interference at the other end. At the point P, there will be interference, and interference leads to a fringe system, that is depending on the phase, we will have intensity maxima or intensity minima. So, due to the finite width of the slit, please see this, due to the finite width of the slit, there is a path difference between waves emanating from any 2 point sources in the aperture of the slit. The corresponding phase shift depends on theta, because as I have shown you the phase shift here. So, this is path difference. So, to get the phase shift you simply multiply it by k into delta gives you the phase shift, phase difference. So, there is a phase shift depends on theta, and therefore, the intensity at point P depends on theta. We will discuss this further and get an expression for the intensity distribution of a single slit diffraction. But before we go that, we want to discuss two regimes of diffraction. There are two realms, two types or two kinds of diffraction. Basically, they are the same, there are no two types, but actually there are two realms of diffraction depending on the distance from the source to the aperture and aperture to the screen, and we will discuss this further. So, there are two types of diffraction, two regimes of or two realms of diffraction. Basically, diffraction is the same, but we have two approximations you could say. So, there are two types of diffractions. They are called Fraunhofer diffraction and Fresnel diffraction. If the source of light and the observation screen are at a large distance. So, let's look at this first. If the source of light and the observation screen are at large distances from the diffraction aperture, so that the wavefronts arriving at the aperture and the screen may be considered plane, then it corresponds to Fraunhofer diffraction. Now, let us see the figure. So, what it means is, if the source, here is the aperture, here is a slit, the aperture is here, the source when it is sufficiently far, when it is quite far, then the wavefronts, of course, even if it is a point source here, it starts with curved wavefronts, but when the distance becomes very large, as you can see, the wavefronts are almost plane here. Plane wavefront means the rays which are reaching the aperture can be treated as parallel rays or nearly plane wavefronts. So, we could consider this as parallel rays which are reaching the aperture. Similarly, if the screen is very far, we are interested in finding out the intensity at a particular point P, let us say at a particular point P. Then from the slit here or from the aperture here, the rays are coming out in all directions because they act like point sources. However, the rays which are reaching when the screen is sufficiently far, the set of rays which are reaching a particular point P can be treated as almost parallel, and therefore, the wavefronts can be treated as plane. Now, we repeat what we have read. If the source of light and the observation screen are at large distances from the diffraction aperture, large distance, so that the wavefront arriving at the aperture and the screen may be considered plane, then it corresponds to Fraunhofer diffraction. So, almost parallel rays. Now, on the other hand, if when the wavefront, when the separation between the two sources, so let us read again, when the separation between the source and the diffraction aperture and or the diffraction or at the slit and the observation slit. So, when the separation between the source and the diffraction aperture or the observation screen, so or the observation screen, this has been repeated here, or the observation screen are not large enough, the curvature of the wavefronts must be taken into account and the plane wave approximation cannot be used in Fresnel diffraction. So, let us look at this. Now, the source is relatively close and the source is emitting light in all directions. If it is a point source, we can represent it by spherical wavefronts, and when the wavefront is reaching here, they are still spherical, we cannot treat it as a plane wavefront. Similarly, if you see at the point P, the rays which reach point P, I have shown the extreme rays which reach point P. So, you can see that it appears as if they are converging to the point, or we have to take into account the curvature of the wavefronts, and then we have the regime of Fresnel diffraction. When the separation between the source and the diffraction aperture and or the observation screen are not large enough, the curvature of the wavefronts must be taken into account, and the plane wave approximation cannot be used in Fresnel diffraction. So, this is the regime of Fresnel diffraction. So, we are focusing on Fraunhofer diffraction, and therefore, let us see a practical arrangement, because I said that when the distances are sufficiently large, but in a practical arrangement it is not possible to have large distances. Suppose you want to do the experiment in lab, then it is not possible to have large separations between the screen and the source and the aperture. So, a practical arrangement to observe Fraunhofer diffraction is shown here. A practical arrangement to observe Fraunhofer diffraction. Let us see it carefully. The source, if we take a point source, for example, if we take a point source and place it at the focal plane of a lens, then the rays coming from the source will be rendered parallel. In effect, the rays which reach the slit here or the aperture here are parallel rays. So, we have met that condition for Fraunhofer diffraction as far as the distance from the source to the aperture is concerned by simply keeping a lens. The distances need not be very large. So, if the lens has a focal length, let us say 5 centimeter, this may be 5 centimeter, and another 5 centimeter you can keep the slit here or the aperture here. Now, on the other side again you have diverging wavefronts which are coming from the small aperture here, the rays are emanating in all directions. Now, what I have shown here, please see the diagram, is a set of rays out of all the rays, a set of rays which are coming at an angle theta, a set of parallel rays which are coming at an angle theta. Why am I picking that? Because in the Fraunhofer approximation, we need parallel rays reaching the point P. So, we are interested in finding out plane wave fronts which are reaching the point P. So, if I consider a set of parallel rays out of all the rays and place a lens here and place the screen on the focal plane, the distance from here to here is the focal length, then we call this as the focal plane. The screen is placed at the focal plane, on the focal plane of the lens. Then all the rays will be focused to a particular point P. So, we have shown that it is focused at a particular point P. Now, why do we go for this? What is this? So, let me explain this a little bit more carefully, and then we come back to the same diagram here. So, if I consider, for example, a lens and parallel rays incident on the lens, then on the focal plane we know that they all focus at the focal point. So, if this distance is f, then all the rays focus to this point here, which is O on the axis. Suppose I take the same lens again here and incident a set of parallel rays travelling at an oblique angle theta, a set of parallel rays, but now travelling at an angle theta. So, where will they focus? On the focal plane. Let us say this is the focal plane, then they will focus, but they will focus at the point. How do we determine? the ray which passes through the pole here or from the midpoint here of the lens will travel undeviated to a point P, and all other parallel rays focus to that point. So, this is the point P where the rays will focus. And if I have a source here, if I consider a set of plane waves or parallel beams which are traveling like this. So, set of parallel rays traveling like this, and if I keep a screen here, so this is the screen, then they will all focus at this point, because the ray which passes through the midpoint here or the pole does not deviate, and therefore, others will all focus to that point. So, provided this is the focal plane. So, what is the meaning of it? Which means rays, each ray, let us say this ray was making an angle theta here, then all the rays, parallel rays which make a particular angle theta are focused at a point P. Similarly, here we have another set of rays making an angle theta. So, if this is theta 1, this may be theta 2, in this case it is minus, they will all be focused at a new point P dash here. So, rays, set of parallel rays which are incident on the lens will focus at different points on the screen placed at the focal plane. A screen placed on the focal plane and parallel set of parallel rays making different angles theta will be focused at different points on the plane. Why am I spending some time on this? Is to because what we will determine is the intensity pattern due to a single slit, the angular dependence of the intensity pattern due to a single slit. And if I say that the intensity pattern is theta dependent and every theta uniquely reaches a unique point P on the screen, then it is sufficient for me to determine I of theta here, I of theta, then I get the corresponding intensity pattern on the screen. So, that is why I have shown this diagram. So, let me put the pre-drawn diagram here. So, I will come back again. Out of all the rays or plane wave fronts traveling in all directions after diffraction at the aperture, the red colored rays represent a set of parallel rays making an angle theta with the axis. They will focus at a point P. So, now let us see. So, the intensity distribution, therefore, the intensity distribution on the focal plane here. I just showed you rays coming at 3 different angles. So, I have drawn a diagram here, a clearer diagram. Simultaneously, I have shown all the rays. So, parallel rays here in black color reaching the point O. This is our familiar focusing, the parallel rays focused onto the point O along the axis. If you put parallel rays tilted, it reaches a point here, and if you put parallel rays tilted in a different direction, it reaches a separate point. Therefore, here it is. Every point P on the screen corresponds to a different angle theta, and the intensity distribution, if this is the x direction, the intensity distribution along the x therefore will be identical to the intensity distribution if I of theta, where theta represents the angle at which the rays are coming out from the aperture. So, the lens does not introduce any additional path difference or phase difference among the interfering parallel set of rays. This is an important sentence. So, I just want to explain this sentence a little bit more. So, because there is a diffraction pattern which is coming here. So, we showed the practical arrangement here for observing Fraunhofer diffraction. There is a diffraction pattern which is coming beyond the aperture here. Now, we have introduced a lens, and how do we know that the intensity pattern that you get here is not affected by the lens? It is not affected by the lens provided the lens does not introduce any additional phase difference. So, that is the statement which is made here, the lens does not introduce any additional path difference or phase difference among the interfering parallel set of rays. I will explain this a little bit more. Now, consider a set of parallel rays which are incident on a lens. So, there is a lens, a set of parallel rays, which means parallel rays means they are represented by plane wavefronts. What is a wavefront? Wavefront is a surface of constant phase. So, these are plane wavefronts. Now, after refraction through the lens, they will all be focused at the point focus. So, this is the point F. So, they will all focus to the point F. Now, when after passing through this converging set of rays is represented by a curved wavefront. The wavefronts are curved now and they reach this point which is the focus. But the wavefront here represents surface of constant phase. The wavefront here represents surface of constant phase. There is, and all of them finally reach the point F or the point P in our case, but all of them reach in the same phase. If there was or originally if there was a constant phase difference, then that constant phase difference will be maintained here. If all the rays are in phase, then all the rays will reach in phase here. There is, the lens does not add any difference to a set of parallel rays. That is the meaning of this, and therefore, the role of the lens, why do we then need this lens? The role of the lens is to bring the intensity pattern onto a common screen, onto the screen which is quite close. So, the role of this lens in the case of Fraunhofer diffraction pattern is to bring the intensity pattern onto a screen at a practical distance in the laboratory where we can perform the experiment. So, that is the role of this second lens. So, the intensity distribution on this plane is proportional to I of theta, but the diffraction pattern is given by I of theta. So, let us come back to the single slit diffraction intensity distribution. So, here is the diagram. I have left the other part of the diagram because that is only to make a set of parallel rays which are incident. So, please see the distribution here, the intensity pattern. So, which is incident, I have taken a particular set of rays travelling at an angle theta. Please see, there are rays travelling at different angles, but I have taken a particular set of parallel rays reaching a point P F. So, this is the arrangement for the single slit diffraction. The intensity distribution is given by I of theta is equal to I 0 into sin square beta by beta square, where beta is given by pi by lambda into A sin theta. A is the slit width, theta is this angle here, theta. So, this is the intensity distribution. The derivation is not difficult, but it is beyond the scope of the discussion that we have, and therefore, we are interested in the result, and therefore, I am not doing the derivation of this expression here, but I of theta, you assume that I of theta is given by this expression, where I 0 is the intensity for theta is equal to 0. Now, I want to see what kind of intensity distribution that I would get with this kind of an expression. So, I 0 is the intensity at theta equal to 0. So, let us just discuss this here. So, I is equal to I of theta is equal to I of beta, because beta is related to theta, is equal to I 0 into sine square beta divided by beta square, where beta is equal to pi by lambda into a sine theta. Now, first I said that I 0 is the intensity at theta is equal to 0. Now, at theta is equal to 0, beta is 0, but beta is in the denominator, therefore, this is undefined. So, how do we say I 0? Because sin beta by beta, sin x or sin beta by beta, as beta tends to 0, then this is equal to 1. I am sure you know this, that you simply differentiate this, then we get cos beta by 1, and cos beta, if you put beta is equal to 0, then cos beta is 1, and therefore, at theta is equal to 0, I of theta is equal to 0 is equal to I 0. So, I 0 is the intensity at theta is equal to 0. Recall what is theta equal to 0? So, theta equal to 0 means on the axis, that is at the point O. I 0 is the intensity at theta is equal to 0. Now, let us look at the intensity distribution of this. So, there are two functions, one is I 0 sine square beta. So, I can write this as a product of two functions 1 by beta square. We know how sine square, this first function varies. So, if you plot with respect to beta, let us say this is 0, beta is equal to 0 and beta is equal to pi, beta is equal to 2 pi, beta is equal to 3 pi. Then, and similarly on the other side minus pi, minus 2 pi. Then we know that sin beta is 0 for beta is equal to m pi, and therefore, the pattern would look like this. So, it is the sine square x curve. So, we have 0 and in between maxima, 0, maxima. So, this is I 0 sine square variation. So, we have 0, so on. Is completely symmetric. So, this is the I 0 sine. So, this level here is I 0, that is the first function. How would the second function look like? So, let me draw that again. That is a cos square function which I was plotting. So, this is beta versus, so this is 0 minus pi minus 2 pi, pi 2 pi 3 pi. So, so it is 0 here. This is the level I 0. What I am plotting is the first function I 0 sine square beta. So, first function is 0 here, maxima at pi by 2, 0 at pi, maxima at 3 pi by 2, 0 at 2 pi. So, this is the sine square function. So, maxima here 0, maxima here 0 and so on. The second function, which is the second function is, so there is a product of two functions, and I have said this is the first function which I plotted. So, the second function is 1 by beta square, that is like 1 by x square is parabolically increasing and 1 by x square is dropping down like this. So, if this is beta 1 by x square, so here is the 0 level. So, this is x is equal, beta is equal to 0. So, it will go to infinity here and then drop like 1 by x square. So, it drops down to very small values. So, it goes to infinity here. And if you take a product of this at, so therefore, now the product of the two functions is the, so this is now I of theta or I of beta is given by I0 is here. So, at theta is equal to 0, because this goes to infinity, this goes to 0, we have seen that it becomes I0 at theta equal to 0. At any other point, it is a product of the value here and here, product of the value here, that is 1 by beta square into sin square beta, and so on. So, if you plot this graph, then we see that wherever this is 0, the product has to be 0, which means the first 0 will be here. So, the function will vary like this, and then so this is continuously dropping 1 by beta square. Therefore, the amplitude drops down, it becomes maximum, again becomes 0. So, the function becomes maximum and becomes 0, the function becomes maximum and becomes 0. Why the maximas are decreasing? Because this value is continuously decreasing. Unlike the case of an interference fringe, where you have sin square fringes, that is cos square delta by 2 fringes, you have similar fringes in terms of minima, but the amplitude is dropping down. There is an amplitude decaying because of this, and therefore, the diffraction pattern would look like this. So, the diffraction pattern will have a maxima, minima. So, what is the value of this? So, this is when beta is equal to pi. The first minima is when beta is equal to pi. So, this is the intensity distribution due to a single slit, intensity distribution due to a single slit, or I of theta or I of beta. Now, we are interested in finding the positions of minima, minima and maxima. So, the central maxima occurs at beta is equal to 0, that is theta is equal to 0, which means on the axis of the slit. So, let us see the positions of maxima and minima. So, the position I of theta, so here I of theta is given by I0 sin square beta by beta square, beta is this. Positions of minima are given by, when the numerator is 0, sin beta is equal to 0, except when beta is equal to 0. We have already seen this discussion. At beta is equal to 0, it is equal to I0. Otherwise, the positions are of minima are given by sin beta is equal to 0, or that implies beta is equal to m pi, except m not equal to 0. That is, for a sin theta, beta is equal to m pi, beta is given by this, which implies a sin theta is equal to m lambda, are the positions of minima, where m is equal to plus minus 1, plus minus 2 and so on. Thus, the first intensity minima will occur at an angle theta 1 from this angle, where if you put m equal to 1, theta 1 is equal to sin inverse lambda by a, and at minus theta 1, when minus sin inverse lambda by a on either side of the central maxima at theta is equal to 0. Now, let us just see a little bit more by putting some numbers. Theta 1, the first minima appears sin theta 1, that is theta min, for the first minima is equal to lambda by a. Now, let us see what kind of numbers are we talking of. If we use visible light, lambda is approximately equal to, let us say we are taking the blue green region, then lambda is equal to 500 nanometers, which is equal to 5 into 10 to the power of minus 5 centimeters, that is 0.5 micrometers, or 5 into 10 to the power of minus 5. Let us just see as an example, this is just example. And let us say A, the width of the slit, typically if A is equal to 1 millimeter, for example, A is equal to 1 millimeter, or second then we have lambda by A is equal to 5 into 10 power minus 5, 1 millimeter is 10 power minus 1 millimeter, then minus 1. So, this is equal to 5 into 10 power minus 4 radians, minus 4 radians. Therefore, theta, this is very small number, this number is very small, and therefore, theta sin theta, this is a very small, sin theta is a very small number. Therefore, we can easily use this sin theta nearly equal to theta, where theta is in radians. This approximation is a very good approximation because sin theta is extremely small. If you use A is equal to 0.1 millimeter, 0.1 millimeter, even then you will see lambda by A is equal to 5 into 10 power minus 5 divided by 0.1 millimeter. So, 10 power minus 2, which is equal to 5 into 10 power minus 3, which is still very small, sin theta, this is sin theta, and therefore, we can easily use the approximation sin theta is equal to theta. Now, what is theta? Theta is the angle corresponding to the maxima, corresponding to the minima in this case. Please look at the interference diagram. Theta here is the angles where the minimas will appear, and therefore, the first thing to note is whatever intensity distribution that we will get. So, I have just drawn the intensity distribution for you here. So, here the angles where they appear are very, very small. In other words, if you see this on a screen, if you see the diffraction pattern on a screen, then you will see that the maximas and minimas are closely packed, and therefore, in a practical experiment you will have to keep the screen sufficiently far if you want to see the maximas and minima. So, let us see the experiment, let us see a simple single slit diffraction experiment. Now, what I am going to show is the single slit diffraction experiment. So, in a simple laboratory arrangement, what we have here is a helium neon laser. This tube here is the helium neon laser tube. So, as you can see here that there is a diffraction pattern which is coming on this paper here, paper screen, but since the diffraction pattern comes at small angles, we have to take it backwards. So, I take the paper back, then it is becoming more and more clear that there is a central maxima and there are minimas on the other side. So, now I leave it on the screen, reducing the slit width. So, you start the diffraction pattern coming slowly, and as I reduce, again you can see the intensity maximas and minimas, and the two adjacent minimas about the central maxima are spreading outward. So, the diffraction pattern is spreading, and as I close it, the intensity reduces, the central maxima becomes very wide, and again if I open the slit, they start coming down. So, through this demonstration what we can clearly see is what the diffraction pattern is and how the diffraction pattern spreads as we change the dimensions of the slit. So, what we have seen is as we reduce the width of the slit, then the diffraction pattern spreads. The two minima on either side moves away in angular spread. Spreading, we are talking in terms of angular spread, and if we open the slit, then the diffraction pattern shrinks, and if we completely open, then the beam will pass through the slit.